speeds, you can think like in general, like rate times time is equal to distance, right? And so if we're finding speed, we can take like the distance traveled divided by the amount of time. There's two different ways we can calculate speed. If we are on a circle, we can either measure how fast the angle is moving or how fast the distance on the outside of the circle is moving. So those are the two different types. So if you have a point P on a circle of radius r, we know the distance the point moves on the outside of the circle, that's s. So if I want the linear velocity, so how fast is this point moving on the outside of the circle, that's your arc length divided by time. So linear velocity is denoted with a v. We've already seen s before. S we know is arc length or distance on the outside of the circle, t is time. When you see these, that's what you typically think of when you think of speed. So it might be like miles per hour, inches per minute, centimeters per second, those types of units. So a linear distance, inches, feet, meters, centimeters, miles, something like that, divided by a unit of time. We could also talk about that same point if instead of measuring how fast it's moving on the outside, I was measuring how fast the angle changed. So if I'm looking at how quickly this angle changes in a given point in time, that is omega, angular velocity. So it's this curved-looking W. It's just another Greek letter. But it's just your angle divided by time. So this has to be, your angle has to be in radians. So it'll be like radians per second or radians per minute, but it will always have to be in radians. If it were anything else, we would have to first change it into radians to get there. So those are the two new calculations that we're going to be doing. They are related. If we go back to what we already know, S is equal to R theta, right? So the first formula, V equals S over T. I could replace my S with R theta. Okay. So then I could rewrite this as R times theta over T. But theta over T, on the last slide, what did it tell us theta over T was equal to? Yeah. So that bar omega. So that is the third formula, just telling us how to relate the two. All right. I gave you, did you guys have everything you needed? This is the table that's given in the book. On your formula sheet, I don't give you this one because it's not really needed. It's just kind of in between step. But on the formula sheet for the test, all three of these would be on there. And so it gives us everything we need. My suggestion to you, we've kind of been practicing this in all the problems we've done. When you read a problem, make a list of what variables you have and what they're equal to. And that way when you're trying to pick a formula, you can pick your formula based off the variables that you have. So at this point, all of the formulas we have, S equals R theta, V equals S over T, V equals R omega, omega equals theta over T, and our area. So here's our list of formulas that we can use to solve any problem now. So let's take a look at one. Suppose that P is on a circle with a radius of 15 inches. So I'm just going to get in the habit. Every time I see something, I'm going to write it down. Radius is R. So my radius is 15. Ray OP is rotating with an angular speed. Which variable represents angular speed? W. Omega, the curved-looking W. Pi over 12 radians per second. Okay, A, find the angle. What variable is an angle? So theta is what I'm looking for. Generated by P in 10 seconds. What's 10 seconds? Okay, first thing, you should always double check your units. This is seconds, this speed is radians per second, so I'm okay. But if one of those was minutes, we would have to make sure we converted them to be the same. All right, so I need theta. So I'm looking at my formulas that involve theta. All right, S equals R theta. Do I have S? Okay. Omega equals theta over T. Do I have omega and T? Yes. So that's the formula I'm going to pick. I like to write down what formula I'm using. It just helps me stay on track and make sure I don't get anything confused. And I apologize if I didn't leave you enough room on here. So my omega is pi over 12 equals theta over T, which is 10. So if I'm solving for theta, I just multiply over my 10. So 10 pi over 12 would reduce to 5 pi over 6. An angle is radians. It doesn't need any units on it. All right. B. Find the distance traveled by P along the circle. The point is moving on the outside of the circle. So if I want the distance it moved around the outside of the circle, what variable is that? S. Okay, so look at what we have. I need a formula with S. S equals R theta. Do we have R? Yeah. Do we have theta? Yeah, so I could use that formula. So R is 15. Theta we found in part A to be 5 pi over 6. (25 pi over 2). What would my units be on that? Inches. Arc length and your radius will have the same unit. Beginning we knew the radius was 15 inches, so this is also inches. Alright, C. Find the linear speed. Linear speed is what variable? So I'm looking for V in inches per second. Okay, so we need V. V equals S over T. Do I have S? Yep. Do I have T? Yep. V equals R omega. Do we have R? Yeah, we did at the very beginning. Do we have omega? Yeah, I think we did, didn't we? Yeah, so technically you could use either one of those. We have the information to do it either way. So do you want to do the division or the multiplying formula? Multiplying. Okay. We'll get the same answer, so there's no right or wrong, but I'm just showing you this is why, another reason why I like to write out my formulas, because sometimes there's multiple ways to get there. So at the very beginning, it told us the radius was 15, and the omega was pi over 12. So that gives me 5 pi over 4. On the units on this, my radius was in inches, and it was inches per second. The units can be a little bit tricky. Some people like to write them in the problem, but some that's confusing. You know, your radius was 15 inches. My omega was pi radians in 12 seconds. Radians is like that extra unit. If you have too many units, it goes away. If you don't have a unit, that's what it is. So my radians would disappear and we have inches per second. Some people like to write that out. Some of us just kind of get a feel for it. We know that R and S always have the same units. Theta is always in radians. Omega is always radians per unit of time. So as we go through some of these, we might kind of catch on to some of those patterns as well. What questions do you guys have for me right now? Let's try another one then. This one is very similar. Do you think you could maybe try it on your own? See, if you get started with part A, you'll probably be okay with the rest of it. The radius is 5 inches. So it looks like everybody had that. But we got stuck on what this 120 revolutions per minute meant. What does a revolution mean? A full circle. So if you go around 120 times, can you tell me your angle? We want it in radians or degrees? Radians. Every time you go around, how many radians is it? 2 pi. So if I go around 120 times, that would be 240 pi. So now we have our angle. Per minute, so what's my time? 1 minute. Okay, that's what that little blurb was telling me. So now let's talk through part A, and then maybe you guys can try B and C. Find the angular speed. What variable is angular speed? Yeah, the omega, the W-looking thing. In radians per second. Okay, so we have to be a little bit careful here. We know omega is theta over t. So my omega equals my theta, 240 pi, per, okay, my time is 1 minute. But I said I want it in seconds. So what should I do instead of 1 minute? 60 seconds. And so then we get 4 pi, right? 4 pi, and that would be radians per second. My numerator was radians, my denominator was seconds. Okay. So if you look at part B, can you find the linear speed now? Take a second. Linear speed is what variable? So we have V equals S over T. I have T, I don't have S. Or V equals R omega. But we have both R and omega. You could get it either way. We have the information to find S, but there's no reason to do extra work. We could just stick with this. So we knew our R was 5 inches. My omega was 4 pi radians per second. You don't have to include your units there, but I'm doing it just to show you. When you multiply these, we get 20 pi. Inches times radians just becomes inches per second. All right, did you guys get that one? Okay. Let's try a couple more. A satellite traveling in a circular orbit 1,600 kilometers above the surface of the Earth takes 2 hours to make an orbit. The radius of the Earth is approximately 6,400 kilometers. All right, so let's figure out what information I just gave you. 2 hours would be the, okay, the 1,600 and the 6,400. The picture helps a lot with that. Here's the center of the Earth. It's 6,400 to get to the edge. The satellite is another 1,600 beyond that. So what have I given you? The radius, we just have to add those together. And so that would give me 8,000 kilometers. approximate the linear speed. Linear speed is v in kilometers per hour. Quick check of my units. This is kilometers per hour, this is kilometers an hour, so everything is how we need it. What formula can I use to find v? We have v equals s over t, but I don't have s. Or v equals r omega, but we don't have omega. So that means we're going to have to do a couple formulas, aren't we? So we either have to first find out s, or we have to find our omega. We actually have a little more information than we realized at first. It takes 2 hours to make an orbit. What does it mean if it makes an orbit?
Full rotation.
Full rotation. So my theta is 360 degrees or 2 pi radians. So if I want to do v equals s over t, we said we would have to find s first, and s is equal to r theta. Do I have the information to find that then? Yeah. My r is 8,000, theta is 2 pi. So S is 16,000 pi. So now v equals s over t. Okay, if you want units, s is kilometers, t is hours, so that's just showing you again it is kilometers per hour once we divide these. And we get 8,000 pi kilometers per hour. So it's not always just one formula, not always just one way to get there. Could I have also found omega first? Yep, by doing theta over t, and then I could have done v equals r omega. So please show me what formula you're using. It makes it a lot easier for me to follow as I'm looking at these. Part B, approximate the distance the satellite travels. Okay, here's the satellite. The distance it travels is out here. What variable is that? S. I'm finding that arc length. In 4.5 hours, so this is a different time. It's going to spin for 4.5 hours now. So I need S. I can do S equals R theta, but the problem is this theta was only when it was spinning for 2 hours, right? So that wouldn't really be the situation here. What other formula involves S? V equals S over T. Do we know the speed? We just found that, so V is 8,000 pi equals S over 4.5. And what do you get for your S? 36,000 pi. That is just the distance on the outside of the Earth, so kilometers. It's not really the math that's complicated here. It's knowing what information you're given and what formula to use. So please, write out. Neatness will help you here. Write out the information you have, write out the formula you're using, and then evaluate from there. Let's try one more for today. Find the angular speed. Angular speed is what variable? Omega, the W looking thing, of the minute hand of a clock. Okay, I gave you like no information here. but we are talking about a clock, and we know a little bit about them, right? Omega, if we look at our formulas, V equals R omega. Did I give you the radius of the clock? No, and there's no way we're going to find that out. Omega equals theta over T. I didn't give you these things, but I think we can find them. Okay. Theta and T. We just need to pick an angle and a time that go together. So let's pick a nice angle. Let's say 2 pi. If I choose 2 pi, that means the minute hand went all the way around the clock. So how much time has passed? 60 minutes, or could you do 1 hour? Absolutely. Okay, so if I set it up like that, that would give me pi over 30. What would my units be? My pi was in radians. My denominator was in minutes. Now, if you had done the 1 hour for your time, you would get something different, right? Which is why the units are important. If you did that, you would have 2 pi over 1 or 2 pi radians per hour. Okay, could you have also done it in terms of seconds? Absolutely. And you would have 3,600 seconds. So you would get pi over 1,800 radians per second. So units are important there. All right. I'm stopping here for today. I know we have 1 example left on here. I might throw in a few more examples tomorrow depending on how we're doing. So I have the papers that you turned in yesterday. I want to give them back just so you can kind of see any comments that I made, any mistakes that you're making. I have the homework for this section. You're going to have a lot of class time tomorrow to work. So we'll do some examples and I will give you guys a lot of time to work and ask questions. So planning for this to be due, let's see, today's Tuesday, right? So probably Thursday, unless we have problems with it, and then we can push it to Friday if we need to. So right now I'm thinking this handout will be due Thursday. Tomorrow we'll finish it up and do more examples and